good morning, dobro jutro, dobro ranko. Okay, so we have today not an easy goal, but the first remark would be we have a classical distribution like in the classroom. So the people strive to go between the end of the room and not in the front. I don't use any presentation here because this is the way how I teach anyway. This talk is not only open-end talk, this is even open-run talk because I used to communicate with the people during the lecture. So I have several scenarios. I'm not fixed what I will do with you today, but somehow the goals are clear and they are not easy. I would like to explain you to some extent how science works, especially with the focus on the role of mathematics and computer science in science. And then in the second part of the talk, I would like to discuss with you a little bit the education and what does it mean to educate science properly. Okay? Okay. Please, there are 3 chairs here, exactly waiting for you, okay? So, maybe let us start with thinking about what is science about in relationship to mathematics. So, in science, we somehow try to generate knowledge. And this question, how we do it, we have in fact 2 basic instruments for that. One is observation and experiment, another one is mathematics. Okay? And then let us think about what is mathematics first. So, I say always mathematics is a language. Now this is true. Mathematics was discovered because if you want to have some kind of objectivity in science, then you definitely need a language with unambiguous interpretation. You think about objectivity, it is not allowed that people saying the same are thinking something different. So you need a language. If you learn the language and you understand the language, you always understand the same as what the other try to communicate. Okay? So the first purpose of mathematics was creation of language with unambiguous interpretation. So everything what you want to express, you can express in an unambiguous way. There's only one interpretation for everything. This was the first purpose. And the second purpose was to develop a language with verifiable argumentation. Okay? So the reasoning must be verifiable. These are the 2 basic points and reasons why people develop mathematics. Okay? And from the very beginning, the mathematicians strive to develop something really perfect. So it means they tried to develop a real language in which they would be with the time able to describe everything from the reality and to analyze it. Okay? Because this thinking, verifiable thinking, I spoke about it, means that you are able to use this thinking to analyze. To analyze everything what you are able to express in mathematics. So you have always these 2 things. Okay? You try to express things, you try to describe the reality, and you try to make research with this. Okay? And their hope was really in 2 parts, I will say, and I will repeat it several times in the history, to describe so much as possible, and then to believe everything we are able to describe, we are able also to analyze. If we are able to transfer something in the language of mathematics, then we are able also to investigate it there. Okay? And the very beginning of this story was, for instance, the school of Pythagoras. You know, in the, maybe, let's say, 2,500 years ago, the mathematics did not have the power as it has today. There was no probability or no infinity, or at least not in the sense as we understand it today. But it was geometry, and it was working with numbers, arithmetic, okay? And there was some theory about that. And already that time, and this was maybe a surprise, already that time, people believed that the mathematics they have is already so powerful that they can do everything what is doable. They really believed with the mathematics they have, they are able to describe everything from the world. It's only the question, find the way how to do it, and then they are able to analyze everything. And this was, for instance, the reason why the Pythagorean believed that everything is describable with natural numbers. Maybe especially for the non-mathematicians, I will tell a little bit about this, because this was, I will say, the pre-stage of developing algebra. Okay? You know what natural numbers are, I think, so 0, 1, 2, and so on. And then they already used the arithmetic operations for sure. And what they observe is what all can be created with arithmetic operations over natural numbers. And they fix their rational numbers. Okay, I think there are for sure many people here who are not mathematicians, okay? But I will show some very small example to understand what I mean this. Let us take a rational number. Each rational number can be represented using two natural numbers, p and q, okay? And you take, for instance, multiplication of two of them, and you know what it is. This is this, okay? And this one is for sure, again, rational number, because you can express it that the ratio of two natural numbers. So you can describe each rational number as a pair of two natural numbers, okay? And you can take any operations, you always will get, if you take two rational numbers, you will again get rational numbers. So the system was closed. They say, okay, natural numbers are natural, they are here, okay? Arithmetic operations are also something natural, they are here. Putting everything together, close the system, this is what we can get, and there is nothing else. Okay, and this was the reason why they believed they can describe everything with this system. And you know the story, then somebody came, very unlucky man, with this root of 2, and proved that the root of 2 cannot be expressed as a rational number. So there is a number which was natural, because natural in that sense that if you take the rectangle with size 1, 1, then this one size is root of 2. This was the way how to define this number. And then he proved in this verifiable mathematics that this number cannot be expressed in this way. And you know what happened then, man? They killed him. Because, yeah, mathematicians can be also aggressive. So it means it was easier to kill him that time than to lose the great theory and the great illusion they can describe everything with the natural numbers, okay? But why I am telling this story? There are many such stories in the history, not always with killing, but almost. But I mean, what I want to say, mathematics is not done. Mathematics is developing all the time to have more expressive power, to get more argumentation power. And already in each stage, also many people today believe, oh, the mathematics is very powerful and doing all everything. It's not true. And to understand what does it mean to develop mathematics, this means to develop a language, okay? So, because what are the basic stones of a language? The basic stones are words with a semantic, with the meaning of the word, okay? So what they were able to fix were numbers, natural numbers, arithmetics, and some principles of geometry. And many people believe that mathematical axioms are claims which we are not able to prove, but we believe in that, and this is wrong. Mathematical axioms are definitions of intuitive notions. So of the basic word, you build your language. So it means you have then the definition of probability, you have the definition of infinity, and so on. All are axioms. Okay? And you can increase the expressive power of mathematics if you bring new axioms into the mathematics. Two notions, they enable you to speak about things you are not able to speak before. Okay? You must understand that this kind of mathematics I started to speak about, without notion of infinity, limit, or probability, was very restricted in comparison with the mathematics today. But we don't know what we have in 100 years about it. Okay, so let us stop for short on this, and I will come also in this ancient time to computer science, because many people in computer science is something completely new. Now it is hip and everybody wants to do it and I don't know what. But the roots of computer science are as old as of mathematics. Let me start. There are two roots of computer science. The first one, about 5,000 to 6,000 years ago, Mesopotamian, Babylon, 10 to 6 inhabitants, okay, and then the inhabitants had some properties, some duties, for instance, paying taxes and things like that. Big data for the time, the first crisis of big data in the history of human history. Yeah, I hope you know what is big data. Big data does not mean you have many data over some specific number. Big data means you have so many data that your technology is not powerful enough to work with them and to bring all the information which is in the data to you. This is big data. And that time they had big data because the only one way to save information was in the head of a man. And if you have really 1 million people, and you have to have all the information in the head of you men making the business, then it does not work, okay? And the consequence was that they developed writings. So to develop writing is a computer science task. This is the first step in digitalization, because if you think about what digitalization is about, it's nothing else as described everything in discrete way as a sequence of symbols. And writing is nothing else. You fix an alphabet and you describe everything as a sequence of symbols over this alphabet. Okay? So it means, I say always, the computer scientists are experts in developing writings, because this was pure computer science task. You have to develop alphabet, you have to develop coding of everything you want to speak about as a sequence of symbols, and you have to develop a system in which you are able to find your information quickly and make some update. This was a database, what they developed that time. From our point of view, it was a database. Okay? So, and if you continue to think in the history, I will say security and cryptography, these are also big topics of today. They are 3,500 years old. All these cryptographic protocols, archaeologists were able to find out 3,500 years old, and it was about cooking. They wanted to hide some recipe for cooking, so these are different stories. But 2,500 years ago, in Egypt, Palestine, China, Greece, they had already very well-developed secret writing systems. So I think this is very old story. And another root of computer science, which is still older, and which is also crucial for our thinking now today, is related to algorithmics. And I mean, if you think that algorithmics started with a computer, you are completely wrong. Because the original way how the people work from the very beginning was the following one. You generate knowledge. But this is not only in order to understand something, this is especially because you want to reach your goal. And if you want to reach your goal, you usually use this knowledge to develop some procedure how to do it. Some procedure how to create some instrument, some procedure, healing procedure, whatever you need. Okay? And what was the specialty before was the following. You generate knowledge, develop some kind of procedure as a sequence of steps, and then you delegate to perform these procedures to people with much lower qualification as you have. This was the automation from the very beginning of the existence of human civilization. You were able to bring the knowledge to everybody. Some very simple example I will take from mathematics from ancient time. You know for sure the theorem of Pythagoras, okay? It's well known. And then you know some small example of that, and 5 to 2 is equal 4 to 2 plus 3 to 2, okay? This is special application of Pythagoras. This was a technology for building, because for sure if you build houses, you have to be able to make the rectangle. And you do it simply taking 4 pieces of rope of the length 5 for 3 units, making a triangle of that, and then you know you have it here. And for sure everybody working on building houses did not need to know why Pythagoras is true and how Pythagoras discovered it, but he was able to apply it. It's a very small example, but telling what I try to tell you. Okay? The automation was the source of efficiency of human civilization since ever. There were not computers at that time, but the performance of these procedures developed were distributed to everybody because it was much easier to perform them than to create them. And this is everything. Okay? So what I try to say with that is that computer science was, let me say, accepted as independent discipline in the moment when we needed specialists on this topic, but not because it was new at that time it was developed. I will come later to this point. Okay, so if I still stay in the ancient time, that may be some small example, because, you know, for sure the science was in very early stages of development at that time, but it was surprising, extremely surprising, what the people were able to do with that instruments they built that time. For instance, the old Greeks were able to measure the size of the earth. They were able to measure the distance to the month. They were able to measure the size of the month. I will show very shortly one of these examples, because it is fantastic what they really were able to do 2,500 years ago with very simple mathematics. And I think these are also the examples you have to have in the schools. I know that you don't have, but you have to have, because then you understand what it is about. So, let us take the earth and let us take the sun. Okay? This is not a sun. And the first assumption they take that the light is coming in parallel because it was very far. They didn't know how big it is. This was not a point there, time, but they're coming in parallel. And then they organized the following experiments. So this is the Earth. Let us say the sun is coming on the 12 o'clock, exactly at the equator. So there is no shadow of this piece here. And then you take another stick here, okay, coming with the light here, and you get some kind of shadows here, okay? Then you can measure. So I will approximate in this way as a triangle, okay? And then if you prolong these two parts here, that the geometry that time already tell them that this angle is exactly the same as this one, because these two lines are parallel, okay? So they were able to measure this angle, and then they took a hardware and measured the distances between the cities here, okay? And if you know the proportion here, and you measure this distance, then you can complete this one. And this was all. But it was genius, and they did. And the measurement is maybe about, I will say, 3% wrong, which is a fantastic result for that time. And you think how hard it was measured, distance about a few thousand kilometers, they did there, okay? And the reason for this unprecision, I will say, was not because they were not able to measure so exactly this part. The reason was that this city was not completely in the north of this city. You understand what I mean? Because if you make a cut of the air, two-dimensional cut, and this does not work because this is somewhere here, and this was the case, then you measure a little bit more distance and it is true. And this was the reason for that, but not otherwise. But it was fantastic what they were able to do that time. So this showed how mathematics became really the powerful instrument of discovering something about the physical world. Okay? Okay, so let us move from this very ancient time and then somehow let us meet these two developments of mathematics, and I will say it's the early computer science. Let us go to Leibniz. Okay? So Leibniz was the first I know who spoke about automation in relation to mathematics. Okay? He said a very famous sentence: the reason to create mathematics is automation. It's very interesting. And the question is, in which framework he thought? Why he tried to say this? And the point is the following one. So he wanted to avoid all fights and all unpleasant discussion about things. Everything should be done in the following way. We take the problem or the reason for discussion, transform this in the language of mathematics. This is described in mathematics. Then we solve it in the mathematics, and then we interpret it back. And because everything in mathematics is verifiable, there is no reason to fight and no reason to strike. Because everything is clear. You have only to do this, and we don't need any committees, and we don't. He really believed he can do that. Okay, you say, okay, this is not really doable, but this was his hope. Okay, this was why he loved mathematics. But this is not the whole story. The whole story, the important of the story is the following one. First, at that time you had this arithmetics, and arithmetics was calculation. If you take the axiomatics, what is the axiomatics? Telling you which are the rules, which are the laws you are allowed to use, and for sure, everybody of you is able to check whether some calculation is correct. Okay? Assuming you master the basic mathematical operation. So you can take it and you can really check whether it is okay. Yeah? And then his idea was to do the same with thinking, with argumentation. So he asked for something we call today logic, because logic did not exist at the time. He asked for rules like the rules for working with numbers for thinking. He asked for expressing what does it mean to think correctly. And now, this was the initiation of very important story in mathematics, okay? Because they wanted really to formalize the way of argumentation in such a way that everybody can really easily, even algorithmically, verify, following some fixed algorithm, whether this thinking is correct. Okay? And then you have to understand some very important thing that most mathematicians even don't understand. How mathematics build the axioms, how is able to mathematics take something which he thinks this is important, I need this word in the language, I think I know what it is, but how to bring the mathematical definition of that, okay? Because this thing you would like to formalize, like what does it mean to think correctly? This is not formal mathematical definition. This is my intuition, my imagination of what does it mean. And how I can bring it to the mathematics, to a mathematical definition. This is the point. And then the crucial point is that in mathematics, if you formulate axioms, you always move from semantics, from meaning, to syntactic rules. So his idea for Leibniz was to express correct thinking and correct argumentation in the same way as you calculate with numbers. You give only a finite set of rules, what are you allowed to do, which corresponds to correct thinking, and each correct thinking must be available by applying a sequence of these rules. And in this way it's formally verifiable because you can verify each one step, like by calculation. This was the idea of Leibniz. And this idea of Leibniz needed 200 years until we get the first logical systems. They do exactly what Leibniz asked them for. Okay? And you have to imagine one thing. All these stories in mathematics are exactly the same. You take probability. At the very beginning, you have some intuition what it is about. You have some experiment. The experiment has different outcomes, but the starting situation is the same. And you try to develop feeling what probability is about. And at the very end, you want to say formally, mathematically, what is probability to be able to work with it. And the very end, you define syntactic rules and say, if you calculate in this way, that you work with probability. And this is the way how mathematics defines probability. And everything else you take is exactly of that same kind. And you needed huge amount of years to get it. For probability, you needed 300 years from the beginning idea until the definition of Kolmogorov. 300 years, huge time. For infinity, I don't know when the people discover infinity, but for sure more than 200 years until Cantor and Dedekind, until you have an axiomatic definition what is infinity about. Okay? So, why I'm telling this? This is very strongly related to education. Our education today is completely wrong. Because what you are teaching in the schools, and even in the universities, sorry for that, are products of science. You know, some develops something, then the people use 50 years to optimize it and change it every steps. And then it is so complex that nobody understands the genesis of this, and then you teach it to apply it. It's something you can completely automate today. You program it, let it computer to do, you don't need people to do. It was time, people in time of technical revolution was educated to be able to do this calculation because there were no computer, and they played the computer that time. This was the automation in time of technical revolution. Today, this is not allowed to be gone. I think if you want to understand science, then you have to learn all the genesis of basic notions, of basic concepts, because this took many hundred years, and to get the final result application is a question of very, very short time in comparison. So we need really to understand the logic of the whole science, to building the research instrument, the ability to describe things, the ability to analyze things. And if you work in this way, then only in this way you can really educate creative people. Not in this way how our school system looks like today. Okay. So let us come back to history. I will now switch to Hilbert. He's a very famous mathematician at the end of 19th and the beginning of 20th century, probably the most influencing one. And he somehow strives to formulate more precisely the dream of Leibniz. Okay, the logic was already here. The word algorithm was even already here. Okay, and the Leibniz say, okay, so we have all this mathematics is a formal system, so it's very clear. This argumentation in mathematics is not only verifiable by human, this is even algorithmically verifiable, because it was all the definitions are done in a syntactic way, as I told you. Like you can verify any calculation, you can verify in the same way any argumentation. Okay? And then it was not so much clear that time what all can be expressed in mathematics. I think this part of the dream of Leibniz was a little bit over already at that time. The mathematicians understand that they are not able to express everything in mathematics, but they tried to express as much as possible. But what they still believed was that their system, the mathematics, is perfect in the sense that everything you can express in mathematics, you can analyze in mathematics. Okay? It's an intellectual challenge, for sure, but it's doable. It depends only on you whether you master it. Okay? So they believe that what you can bring in the mathematics, this is the main point. If you can do it, then you can solve it in the mathematics. This was. Okay? And this was an extreme belief to some extent, because a part of this belief was in fact that for each problem you can formulate in mathematics, you have a mathematical method or algorithm for solving it. And then let me explain what does it mean exactly. A typical problem formulated in mathematics, like, I don't know, solving quadratic equations or solving linear systems equation or whatever, okay, has infinitely many problem instances. Do you understand the problem, the term problem instance? So a concrete quadratic equation is the instance, and solving quadratic equation is the problem. Okay? And typically you have infinitely many quadratic equations, so there are infinitely many problem instances. And to find a method means that you find a procedure that works for each one of these infinitely many instances. So this was, and he believed that for each such problem formulated in mathematics, there exists a method and we have to try to find it. And he he went to a very extreme position. He told even for proving mathematical theorems, there must be an algorithm. It means the input is a mathematical statement, and the algorithm has to produce the proof. It's not only about calculation. Okay? So you get input, a statement, and you want to have algorithms that create proof whether it is true or not, and convince you that this is the case. Okay? And he believed this is doable. Okay. And then you may know, okay, yeah, now I start to communicate with you. So what happened after that? I hope I have a few mathematicians here who can say, okay, this does not work and why. So who can tell me now? Or who can tell you? Us now. So, okay,
just was it Gödel that said that it's actually not possible to find solution for all the problems that...
Okay. Thank you. So the right answer is that Gödel says that this is not doable, which from my point of view is happiness, because then we have, if this is not true, and we could have algorithm for proving theorem, so we can close mathematics departments, I think. But, but anyway, but what Gödel really told us exactly? Can you tell us?
I'm not a mathematician.
Oh, okay, but it's great. Then it's great that you told us already that. Okay, fantastic. So, where are the mathematicians here? So, where are the mathematicians? Let to tell us. Gödel proved there are really breakthrough results for whole science about the limits of science. He proved that the expressive power of mathematics, which means what you are able to express in mathematics, is larger than the argumentation power. Okay? So you have a language, the language is called mathematics. And there is more about you can speak about than about what you can argue. It means you can formulate claims in mathematics, and it is not decidable inside of your mathematics whether they are true or wrong. Okay? So the language is not perfect. You can formulate question, task in mathematics, even some like system of some special equations or whatever. Okay? And they are not solvable in mathematics. There does not exist any method for solving them. Okay? And he proved even more. He proved this is a situation forever. You can increase the power of mathematics in both directions, in descriptive direction, in argumentation direction, by bringing new axioms, okay, new words, but also after that the situation will be the same. Maybe you were able to solve something you were not able to solve before, but you, in this new mathematics, you have again the situation you can speak about something you cannot solve inside. Okay? And this result was in fact some official starting hour of computer science, or at least on the computer science theory, in the following sense. Because if the people got this information, that they start to think about, okay, which problems are now solvable and which are not. And they wanted really to classify now. These problems are solvable in mathematics and these problems are not solvable in mathematics. Or better to say, these problems are algorithmically solvable and these problems are algorithmically not solvable. Okay? But if you want to prove in mathematics that something does not exist, it means it does not exist any algorithm solving this and this problem. You want to prove it in mathematics, okay? Then you are in trouble if you don't have a mathematical definition of the term algorithm. Algorithm was a very intuitive term. It was something like, oh, you have some description how to proceed, okay? to get the result. Yeah? And this is not a mathematical definition. Okay? And this was the last axiom in mathematics, I remember. We are waiting for a new one now. And the quickest one, only 6 years for Turing and Church to offer a mathematical definition of the term algorithm. Okay, and maybe 20 years more to start to believe in it. Okay? And I don't know how much time I have still. Okay, I have still enough time. Also, maybe I can a little bit go inside and try to tell you how such procedure as developing an axiom does work concretely, okay? So what would be your intuition? What is algorithm about? I think not mathematical definition. How you would describe the term algorithm? No formal definitions. What it is? I already used some synonyms, or maybe you can master that. So I would like to have some proposal.
It's a sequence of steps to solve a problem.
Okay, this is a right starting point. You describe the algorithms as a sequence of some activities, and you call these activities steps, okay? So what do you need if you want to fix this term? You know already that it's a sequence of some steps, but what do you do need?
Conditions.
Some constraints.
On what?
Constraints on some problem.
Not really constraints, but I agree with your definition as a sequence of steps.
Yes.
But you have to tell us what the steps are. This is still abstract. So what are the steps?
It's computed from some input to output.
Okay, you say some functions in some sense or whatever, okay, so, or some operations or something like that.
It should be like clearly defined. Like one step is like clearly defined, one type.
One step should be something elementary, something everybody is convinced we can do it, okay? So, but what you need now still is what? You have to exactly tell what are the allowed functions or operations which are considered as a step. You have to take a finite set of some activities which define your steps. You agree, okay? Because you proposed. I have to ask you.
So comparisons. We can do comparisons.
For instance, you can compare some numbers, you can multiply, you can do also some text operations, whatever. But you really need to fix this set of operations. And then it is done because you have your set operation and you say, okay, every sequence of these steps is an algorithm. And then what is the trouble on this? Because this you can do it 5 minutes as we did now, is to stop sometime and say, okay, I have all important operations in my set. Because maybe there is some I will define an algorithms over a set of operations, okay? But maybe there is some operation which is very natural and doable. I don't have it here, but this can be expressed with the operations I already have. And this was the problem of them when we are allowed to stop this. Okay? And this was not so easy to master because later we have this quantum computer which is completely different set of operations. Nobody thought that time about expressing them in that way. I will tell about this later still. But, okay. And then how to do it? Because, you can always say, okay, I think these are natural operations. I have algorithms over this set of operations, but I'm not allowed to say that I am done because maybe my algorithms are weaker than the true algorithms because I'm missing some important operations. Okay? And then the Turing went, in fact, 5,000 years back and started to think in the term of digitalization and in writings and coding and solve this problem on that level. What he did was the following. First, he started with the idea how we work with writings. We described everything, because this was the formal way of mathematics, as sequences of symbols. The digits are sequences of symbols, the texts are sequences of symbols, the proofs are sequences of symbols, the programs are sequences of symbols, okay? Everything is sequence of symbols. And the data as well. And I say, okay, if I have data as sequences of symbols, whatever this is, okay, this is something like that. Okay? And the first step was said, okay, the human brain is restricted, is finite. Okay, this is assumption. You need it. Okay? So, there is some constant telling how much you can see at once, how much you can take in your mind at once, because your capacity is somehow restricted. This is something very natural. He did not try to fix the constant, how big the part is, you can save in your head, but he only said, okay, there is some restriction, nothing else, okay? This is something very important also to imagine. If you have something like, which is infinite, you always, okay, we don't know whether there exists something which is infinite, but anyway, if there would exist something infinite, you always can see only a finite part of that. This is our game, okay? And now, we told, okay, then in fact it means this is restricted to some extent, so it means my operations are restricted for arguments of some length where small c, and I compute some functions of that, and the result is another text. It's fine, okay? And the trouble is still, I don't know how big this constant c is. This may be a very big one, okay? And then to take as the set all functions over some abstract text to abstract text with some length of c where c is unknown would still not happiness. But then he discovered very simple thing. Each such functions can be computed by working on one symbols only, looking on one symbols, saving something small in the memory, okay, to rewrite maybe these one symbols, and you can somehow pipeline this one step from input to output, only working with operation over one symbol, okay? And after that it fixed it, it solved the problem, because he did not need to fix the set of operation, because that in operation can be done in this way, that you have some finite memory, looking on one symbol here, changing something, and then looking on another part of the text and running around. And this results in some kind of formal model having some syntactic rules. And this story was done. Okay? Well, okay, and there are several reasons why the people now believe that the definition is good. Because, you know, each axiom is not provable. If it were provable, it is not called axiom for sure. It is, you cannot prove that your definition of a term is correct, okay? So, why do people believe? Because the people created many definitions in different formalisms, and all reasonable ones were equivalent. I mean, this term of algorithms became the same, does not matter which one you use. And the biggest confirmation is quantum computer. Quantum computer is a computer which is not primarily defined in symbolic way. You take the physical operation of the physical systems and say these are the basic operations, and you can prove that it is equivalent to this guy. Okay? And then this is the main confirmation of this axiom, that this axiom is right, because if you take really the operation, the physicist means that these are the natural operations, and this is equivalent to this thing, then you have a really strong confirmation that it could be the case. Okay? Okay. So we have almost 1 hour done. Well, so this was, let me say, official burning time of computer science. And now the story continued with many development steps. Maybe the most important one is the notion of complexity, on computational complexity. Simply fixing the following. If you work with information, so you have your information, which is always a sequence of symbols. You have your data, and there is some information inside of this data. A part of this information you want to take out. You want to recognize it because they somehow coded, okay? You want to discover it and fix it. And to do it, you have to work, okay? And the computer scientists develop a theory of measurement, how much work has to be done to get this information from this data. Because each problem is nothing else on this abstract level. Sequence of symbols is input, sequence of symbols is output. And the question is how much work is necessary and sufficient to get it. Yeah? I will get a number in binary coding, and I would like to have the factorization of it. Okay, and the question is how many operations I have to do to get all the factors of this number. Okay? And this is some very complex theory. I don't want to go in very special things, but in the fact the situation is like that, the most interesting thing we would like to know, we don't know. Okay? But anyway, the whole algorithmics today is somehow influenced by this thinking. Okay? We have many, many problems where we think that the amount of work to get the information from the data is larger than the energy of the universe. And so you can have algorithms for getting this information, but you are not able to perform it because the time of the universe and the size of the universe's computer is not enough to compute the information from the data. Okay? And then you try to fix what you can do in such cases, whether you can do partial information in a reasonable time. And this is, I think, the main gain of computer science today at all. Okay. Okay. So I tried to give you some picture about what is computer science and what is mathematics about, and what is their role in science at all. Are there questions now to that? Yeah.
Question. So, can you give an example of problems that couldn't be solved by algorithm?
Yes, for sure. Okay. You are from which area?
From biology field.
Okay, good. No, this is good to know. Okay, that's nothing special. Okay. There are different kinds of problems. One of the label of computers, I will tell you at least two, that you have something completely different. So, one question is, you get a program. You know what program is, even if you are biologists, I think. So, program is nothing else than a text over the alphabet of the computer. Yes? Consists of a sequence of some operations or something like that. And then you can put a question, you have some expectation what the program does, and you ask, you want to verify whether this program is correct, and you ask whether this program really computes some specific function f, okay, for each input. And for this kind of task, there does not exist any algorithms. So for verification of programs, whether they work properly, they don't exist algorithms, so you cannot verify automatically whether the program works correct. And this is the reason you have so many bugs in your systems. Okay, this is one example. There are also examples outside of the computer science work. There are some games, like domino game. Okay, let me think about such a game. I will say, you have some domino. Can I say domino in English? I am not sure. Oh, okay. You have two words, one below, one over, okay? And you have a few such pieces. In each one you have something else, okay? Something like that. So you have finite number of pieces of such, let me say, cards, where you have text in upper part and text in lower part, okay? And for each one you can have as many copies you like, okay? And now very easy question. You have to play in such a way to put these cards one after other in such a way that the text written in the upper part is the same as the text written in the lower part. So very nice, easy game. You understand the game. I don't need to bring an example, okay? So, and to find a solution for this game, in general, there does not exist any algorithm. It may look almost unbelievable. You say, but this is easy. It's not. Yeah?
Which the algorithm might return, there is no solution. So
yes, you have, but your algorithm has to decide whether there is a solution or not. And if it's the solution, the algorithm has to propose the solution. This is what we expect, okay? And the reason why, for sure, if you have finitely many these stones and finitely many copies of each, then it must be doable because you try all possibilities. But if you have of each stones infinitely many, okay, and maybe this is 10 millions long, you don't know where you are allowed to stop and say it does not work or it works or whatever, okay? This is the problem in the game. There are some geometrical game. So there are many things you would be surprised. There are even some system of equations, not linear systems of equations, but other ones. And they are not solvable. You will say this is only calculation, what it is about, but it is not. It is really hard. So there are really huge amount for very different kind of these problems, and we can prove there don't exist algorithms for that.
Is it possible that the problem with formulation that we could not formulate our task properly to find the algorithm or the problem?
So I think the question on this level is not, you have always finite, completely formalized formulation of the problem. You can describe the problem very well. This is not on this level. For sure, there are problems which are not describable, and for sure you cannot then solve by algorithms. But this is completely not interesting because if you cannot describe your problem, what it is about. But all the problems are very well defined. You get a text, you have to check whether this is a program. You can still do, for this you have algorithm, okay? And then you have to check whether this program does what you want that the program does, and then it is not checkable at all. Okay? And you have to understand this very properly. What does it mean for science? This does not mean that you can verify a particular program. It only means you cannot automize this, that you have a program that take other programs and check whether they work correctly. Okay? But you can investigate each one program as a specific scientific problem and try to fix whether it works properly or not. But the bad news is that there are even programs for which don't exist mathematical proofs whether they work correctly or not. So there are even instances of programs for which you cannot investigate in the whole mathematics whether they work properly or don't work properly. Okay? And this is only one example. We have huge amount we have to simply, what is the message coming from that? The message is that we are building some instruments for research like experiments and mathematics. They are two basic instruments. And they are never perfect. So the main achievements in science happens in building your research instruments. If you discover the probability theory, you bring much more to the science with any big theorem. Because you bring an instrument, you can make thousands of different things. Okay? So the main point, if you want to understand science, and I say now even if you want to teach science, you have to teach how to build research instruments, not to teach the product of science and you don't understand anything, because all these things, the most of the things we are teaching now, the computer can already do today. They don't need people knowing it. Okay? This is the problem. Okay, so we slowly but surely switch to education, but are there some more questions?
Yeah. Well, perhaps that's to education. Wouldn't it just take too long for the kids at school to discover all these tools by themselves?
Oh.
Because you said that each axiom takes hundreds of years, except for the last one.
Okay, this is an interesting question, but you mean to understand, if it is the case that you need 300 years to understand it, then you are true. Okay? But this is not the case. But definitely it is not the solution that the most important steps in science you don't teach. You simply don't look. You bring a definition, nobody understands why this is done in this way and another one. Even something which is not axiomatic, but very often used to teach already in the high schools. This is limes, okay? This is not axiomatic terms. This is some word in mathematics already derived from axioms, okay? It's not axiomatic. But you get the definition and start to do something with that. It's absolute nonsense. The mathematicians, the first idea of limes came from Newton, and the mathematicians needed 200 years up to Cauchy to fix this definition. And if you say we will not tell anything about that, then you don't understand what it is about. Sorry, even if you are able to make some proofs about it and you make some functional analysis, you don't understand what it is about because you don't understand whether it is exactly as it is and not in different way. And what you have learned in this? Things that already are automized. I'm sorry, but all these systems that make the functions analysis, you have it on the calculator. Why we teach them? I am not against that, we are not allowed to do that. But this is not the right intellectual challenge, because you don't understand what you do. You learn algorithms, which are maybe a little bit more complex, it's not trivial, it's some intellectual challenge, but you learn to apply some algorithms without understanding how they were derived. You teach in the school, for instance, this is very common, system of linear equations. And one of the algorithms is you are allowed to add two equations or multiply some equations. Nobody in the schools, maybe even the teacher, knows why you are allowed to do these steps without changing the set of solutions. And you have really to see the geometry behind to understand what is happening. Nobody show you. What do you learn? Each system is in fraction of second. Okay? This was the way how we used to teach 100 years ago, because we did not have computer, and we needed people qualified to be able to do that, because this was the automation at that time. Some people discover algorithms, and other people use them to calculate during the word wars how to, I don't know, shoot somewhere or whatever. Okay? But this was really the case. But the life is different now, 100 years after. So we are teaching most of things we don't need to teach, because this is only to put something in our brain without really understanding what it is about. This is reality. So what I'm voting now for is really to change the whole educational system and to convince people that we have to start to work on that. And I mean, I understand very well your comment that you say, because this is a game, what I will pay for that if I do this switch, okay? And what I try to say is the following one. It is not so bad as you think about this, because I'm teaching the whole time in the way, and I'm teaching in all levels of the schools and even for sure in the university. And I never had the problem that the people coming from my classes are weaker than those coming from other classes. The opposite is the way. The point is, the first principle, maybe you don't teach so much as you teach, but you teach properly. But this is very general principle. My opinion is always, it is not, the main reason is not allowed to be quantity. It is not question how many biological facts I saw, because in 2-3 years I would not able to remember any one of them if I only save them, not understanding why they are as they are. Okay, I'm not sure what I still remember from my high school chemistry, for instance, because I had a very bad teacher in that directions. Okay, but I always, for instance, I am coming to lectures. As you see, I don't have any presentation. I don't have nothing on the paper. I'm doing all my lectures in this way, for hours, because I know the genesis of the things. I don't to save any details. I don't have it in my head. I derive it always in the class, because I know the genesis. And this is the way how you have to teach the people. Because what is the job of the future? Nobody knows. I don't know as well. But for sure, different as now. And if you look on the rapid development that time, almost everything which is easy, it means low qualification, you don't understand but you save some method, some facts, whatever, will be automized. Definitely automized. The only chance to contribute to society is to be able to make creative work, to continue to further development, either to the automation, or to deriving new knowledge, or to modify and improve things that are already here. And if you want to improve things, the research instruments, for instance, things like that, you have to understand and master the genesis, and then you can get the idea, oh, this can be done better, and then do it. Okay? So we have to educate completely different people. They are really able to do creative work. They have to be trained to do creative work. We have to forget about teaching this huge amount of facts. Okay? And if you look on teaching computer science, I don't know now to speak about this kind of nonsense, how to teach Word and PowerPoint, because this is no science, and this is almost forbidden to be a part of school education at all, because this is something you can learn in some evening courses if you need. If you look on computer science and you want to teach this, okay, the question is, what do you want to teach? If you take a programming language and you say, I want to teach programming, and I will take 300 operations which are there, behind many of them, you have already complex programs, maybe even of more than 1,000 rows, okay? And you teach them what happens if you use that, and then you try to start doing some program, you are completely wrong. Because you, again, are teaching some product of science, which is very complex. You don't understand what it is about, and you try, if I push this one, then it happened this. And if you push this down, it happened this. Okay, so this is some kind of monkey. Monkey can also learn in some system. If they push it, you can banana. So I do. Okay, so if you want to have people like that, fine. But if we teach programming small children, for instance, then we let them to develop the programming language. So it means we start with very few, maybe 10 instructions, because we have to have some words. Programming language is a language, okay, in which you tell the computer what the computer has to do. But if you have only 10 words, it is very hard to tell something, because the expressive power is very small. Okay? So we'll learn the children to recognize that it would be nice to have more words. And then we teach them how to teach the computer to learn a new word, and after that they are allowed to use it, and they develop their own language for communication in computer, and they develop programming in this way. And if you teach programming in this way, at the very end they understand much more than one programming language, because they understand how programming language can be developed. They understand the principle of modularity used in a lot of other scientific disciplines. And they understand that the language is not something which is done, but something which is always developing. Okay? And there are many things. You mean, if you teach in this way, you get always context of many disciplines. People are speaking about interdisciplinarity for, 30, 40 years, but all the implementations are crazy. But it's very natural if you start at the very beginning and try really to follow the genesis of science as much as it is doable, and try to bring full understanding on everything what you do. Okay? Maybe some small example everybody will understand and does not need to be specialist. Let us go to primary school and start to teaching numbers and arithmetics, okay? So usually what they learn in the school is somehow to count, and then to work with number up to 20 with some addition and later multiplication and the larger numbers and things like that. But what you already start is also suboptimal, because you start with decimal representation of numbers. You have 6,000 years of development of number representations. You take the winner, which is the decimal representation, and you start to teach it. Okay. And you can ask, is this really the best way to do that? But you have to think about how people started to work with the numbers. So the first representation of numbers was unary representation. It means if you say today 3 as a digits, that whether there are 3 men or 3 dogs or whatever, but this was the original representation of 3 for people. Definitely this case. Okay? And then after some time they recognize, if you have too many of them, it is not a happiness. Okay? So then you have to do something better, than you get better feeling what it is about. And then they start to develop some kind of units. They say, okay, because of the fingers, this was the decimal system, but no, not always the case. You can count up to 10, and you build some new units which has the value 10. Okay? This is and I will call it now card. Okay? And then I have cards with value 1, with value 10, then 10 minus 10 is 100, and then I express each number as a set of such a cards, if the value of the number is nothing else than the addition of the value of particular cards. This is the first principle, very simple. You are not asked to take the decimal system, you can take anyone. Do you know the first one in the history in Mesopotamia? What were the units there? Does somebody know? What they used? It was not decimal system. No? Nobody knows. It starts like decimal: 1, 10, 60, 600, 3,600. So they multiplied alternative by 10 and by 6. This was the representation of numbers that time. Is working with such cards as well. Okay. And this is the reason why we have 60 seconds, consequence of this ancient time. Only one reason for that, no logical one. Okay? But if you have these cards, the first principle I told you is very easy. The sum of the values on the cards is your value. And the second principle, also very easy and common to all systems, is that your number representation is unambiguous. This is that representation that uses the minimal number of cards. So if you can change 10 smaller cards for one larger, then you do. Okay? This is everything, nothing else, only these two principles, and you build everything, even the original number in Roma, not the advanced one, but the original ones. Okay? And then the addition is very easy. You take your one card set, second card set, put these sets together, okay? And then you minimize the number of cards and you are done. Very simple principle, okay? And if you learn to work with things like that, then you understand at the very beginning all systems. Even later, if you want to teach binary systems, you use exactly that. We even, not the small children, but I think in children in age 5, class 5, 6, 7, 8, or something like that, they are able then develop their own systems, okay? And the next, because what is the core of the story? You learn to work with the cards. You can then try to use operations, and then you can ask which one of the system you use. You can develop several ones. You can let the children develop new ones. And then you ask them to compare them. And they have different criteria. One of the criteria is very important. Whether if I see these cards, I understand approximately what is the size of the number. Because this is very important. Now, if I give you binary number, you don't have feeling what it is about. Okay? The second one, the representation has to be short. Okay, you can compare it with that. And the third one, you have to be able to execute the operations. If you take multiplication of the numbers from Roma, then you are in troubles. This was the reason why the system did not have a perspective. Okay. And then you understand how the people choose the system at the very end we use now. Okay? And the second step, but the problem is in following. This is the first step. And after you have this step, you are trying to find a short representation of your numbers, because this card is not always a nice possibility, because you have infinitely many cards. This is a trouble. Because you have larger number, you need larger units, okay? And you can have many of them. And then the idea came that you put these cards, then you start the smallest here, then the next smallest, and so on. And then you write only a digit, how many they are there, okay? And you get this kind of digital representation we have today. But this digital representation is relating to fixed order of the cards. And then you tell how many of each one, and because you make it in such a way that you never use above some number of the card of the same size, you have finitely many symbols to express this. You have a finite alphabet, and we call this representation position representation, because it depends on which position, which digit is written. And then you understand the principle, how this representation of number was done. But who does it teach in the school in this way? You get a ready product, and you don't, maybe somebody, no? But
I was teaching this way.
oh, great, thank you. Okay. But in this way, you really understand what it is about. And this is a very small example. But I say everything you can do in this way. Really everything. And if you are not able to do it in the way, let it be. Because then it does not have sense. Okay? Then you do, because think about the contents of current mathematics. Why we are teaching this small fraction of mathematics or not another one? And the only one reason is historical one. This was the mathematics we needed in the time of technical revolution. This was when this mathematics, teaching mathematics, was developed. This was exactly what the people needed at that time. Okay? If you look today on really of using mathematics as an instrument, allow me to say that the most used part of mathematics today is stochastic, the probability. I mean, there is almost none, I will say none, discipline that does not need some kind of probability or probabilistic test or something like that, because empirical research is the last step. You can do anything more than you do empirical research. Okay? And then you have to understand the probability. If you don't want to learn some algorithms and not knowing whether they are the proper one for your experiment, for evaluation of your experiment. Okay? So it means, in some sense, the probability must be something which has to come to the school, maybe with some amount of lesson which is much higher than, I don't know which, or the functional analysis, for instance, because you don't understand what the function is about, what the functions are interesting, but you do simply. Okay? So, I mean, the changes are not only asking for the way how to teach, but also the thinking about the contents. But you can get a proper idea how to teach and want to teach if you really look on the genesis of the mathematics. You look what you usually need in the application, what kind of understanding, okay? And then you can try to develop what is available in which age to discover this. And then you have really to revise the complete, not only the way how you teach, but even the goals of teaching each subject. Okay. I think you are biologists, if I remember, yes? So, I mean, this is the same for biology. If I would teach biology, I would not try to tell them this works in this way. I will try really to teach them how the people were able to discover it and how they were able to convince other people that this is working in this way. So I will try really to go in the direction of this experiment of developing these instruments, how they can verify, and why we believe that because we cannot see everything. You know it better than me. So I mean, but maybe you will not need, you won't teach all the facts you are able to teach now, but if you teach only a part of them, but they understand how to discover them, that you did better work, definitely, okay? And this is really for each. Let us think, one other example is physics, okay? I had a very nice discussion in some round with many scientists, and there was exactly one biologist coming and telling, oh, we have a hard life now. We discover more and more important things, and we revise all our theories, and we have to change the curricula for high school students every year. Oh, this is a hard life. And the physicists start to smile and told me, oh, you lucky man. If we would try to tell the high school students what we are doing every year, that this will be the end of the physics in the high school. So, I mean, this is true. If you would start to teach physics with quantum mechanics and Einstein's relativity theory, this will be the collapse of teaching physics in the high school. But what they do is they start with developing the way of thinking from Newton, because this was the first serious point in the history of physics, okay? They start to develop this way of thinking, even if it is wrong. You start with this, you start to understand how to discover it, how to do it. There's also a lot of improvement can be done there, but I don't know, discuss this. But you go this way and do some stage of development, to some age, you are able to explain something and you continue, but you have not the goal at the very end that they understand the newest physical theories. But they have really to get something very basic from the genesis of the subject. It's great. It's exactly the right way to do it. And we have to do it in all subjects we teach, even in the languages. Okay.
So thank you very much.
Okay.